Here we have a linear system of equations that we've been asked to solve using the elimination method. It is linear. Both of the equations are lines with a highest exponent of 1. Now, for the elimination method to work, remember we need opposite coefficients on one of the variables. So as I look at this problem, here is a positive 4x, there is a positive 2x. Those are not opposites. Here's a positive 3y, and here is a positive y. Those are not opposites. So for this particular problem, I'm going to have to create my opposites by multiplying one of the rows by some non-zero number. I can pick any non-zero number that I want that will create opposites. So now let's think. What's the opposite of 4x? Negative 4x would be the opposite of it. What would I multiply 2x by to turn that into a negative 4x? If I multiply by negative 2, it would make this 2x become negative 4x, which was opposite of the positive 4x above. But now, if I multiply part of the row by something, I have to multiply all of the row by something. So now let's come over here and rewrite our top equation that we're not fooling with at all. But let's take the bottom equation and multiply by negative 2. When I do negative 2 times everybody on the bottom, that gives me minus 4x minus 2y equals negative 8. Now, as you can see here in red, the 4x and the minus 4x are opposite of each other. Some people call the elimination method the addition method because once we have those opposite coefficients, now we're going to add the lines together. If I add the lines together, the 4x's will add out, or they are eliminated, and then 3y minus 2y just leaves y. 10 minus 8 gives me 2. So now I know that y is 2. But remember, we've not solved the system of equations by just knowing y. We need to know the point where the two lines are intersecting each other. So let's take this 2 that we've found, and we can substitute it in for y in either of the original equations. I'm going to choose to put it in this equation because that one is a little bit smaller and a little bit easier to work with. So everywhere there's a y, let's put 2 in its place. When I put 2 in the place of the y that is here, it gives us 2x plus 2 equals 4. If I subtract 2 from both sides, I have 2x equals 2. And then when I divide both sides by 2, I have x equals 1. So the solution for our system of equations, the x value is 1, the y value is 2. Let's write an ordered pair, x first, y second. The point 1, 2 is our solution. Now, if we were to draw a picture of this, we would see two distinct lines that are intersecting in one point. When you see two lines, you say that the lines are independent of each other. If they cross at any spot, you say that they are consistent. Now, this one wasn't so hard because I only had to multiply on one row to create my opposites. Sometimes you have to multiply on both rows to create the opposites. For instance, the problem that is here, 4x and 9x, those are not opposites. 3y and minus 2y, those are not opposites either. So now I need to try to create opposites here. Now, you can multiply either of the rows by any non-zero number that you like, but we want to try to make it as efficient and as easy for us as it can possibly be. I notice, first off, that 3 and 2 are smaller coefficients than the coefficients that we have on the x's. So it looks to me like it's a good idea to try to eliminate the y's. I also like the fact that we have a positive here and a negative there. So since I've already got opposite signs, I'm not going to have to worry about trying to multiply by a negative. Now, one thing that will always work to help you create your opposites is to take the number that is here, multiply the other row by it, and then take the number that is here and multiply the other row by it. That may not always be the most efficient way to go, but it will help us always to create our opposites. So let's take the 2 that is here and multiply the top row by it. Let's take the 3 that is there and multiply the bottom row by it. And remember, everything across the row needs to get multiplied. So looking at the top one, 2 times everybody there, 2 times 4x makes 8x, 2 times 3y makes 6y, and 2 times 14 makes 28. Same thing for the bottom row, 3 times everybody here, 3 times 9x gives me 27x, 3 times minus 2y gives me minus 6y, and then 3 times 14, that's going to be 42. Now we have created our opposites. As you see here in red, those y values are opposite. Once we have our opposites, add the rows together. 8x and 27x gives me 35x. The y's are eliminating. That was why we multiplied. And then 28 plus 42 gives me 70. 35x equals 70. If you divide both sides by 35, x is 2. Once I know that x is 2, now I can figure out y by going to one of the original equations. This one seems to have a little bit smaller numbers, so I'm going to choose to use it. Let's take the 2 that we found. Let's put it in for every x that we see in that equation. So substituting 2 in for the x, 4 times 2 made 8. Let's bring down the 3y and bring down the 14. If you subtract 8 from both sides, 14 minus 8 gives me 6. Now if we divide both sides by 3, looks like y is also going to be 2. Now, our ordered pair should be the x value first, the y value second. Can't really tell a difference in those 2's. The x2 is first, and the y that is a 2 is second. These 2 lines have again crossed in one spot. When it is 2 lines, we say independent. When they have crossed in any spot at all, we say consistent. Now, sometimes when we do our elimination, we'll find an interesting situation where the variables get eliminated, but you still have a constant value. For instance, here, I see that I've already got opposites, so I'm just going to add the rows together. The x's add out, so did the y's, and I have 0 on the left-hand side. On the right, 4 plus 5 is equal to 9. Can 9 equal 0? 9 doesn't equal 0, so this means that there is no solution that can possibly work for these 2 equations. Now, if the solution to a system of equations is the point where they are intersecting and these don't intersect, then that means that they are parallel lines. Parallel lines have no solution. When there are parallel lines, we say that the system is inconsistent. Inconsistent means no solution. Now, there still would be 2 lines, so we would still say that it is independent. Inconsistent, independent. I remember this by putting the I in inconsistent and the I in independent side by side. If you think of them side by side, they would look like parallel lines. So inconsistent, independent means parallel with no solution. Well, what if everything went away? If you had completely opposite things all the way across on both sides of the equation, like we do here. Adding the things together, the 6's add out, 6x's add out, the 4y's add out, the 10's add out. Since everything is adding out, you've got 0 on the left, you've got 0 on the right. That's always going to be true. That means that what we've really got here is the same line, just written in a different way. This has an infinite number of solutions. Anything that works in one equation would also work in the other equation. If you were to draw a picture of it, you would only see one line since the lines are on top of each other. When we only see one line, we say that it is dependent. The lines have still crossed each other, so consistent will be the word that we use to describe our system, but the lines are dependent. If the lines cross in any spot or in every spot, say consistent. When it's one line, say dependent. If it's two lines, say independent.